Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Hello everyone, welcome to today's video. So today we have brought again the interesting topic of industrial problems where your theoretical knowledge will meet the practical applications. We have already launched an first episode of this topic, real life industrial problems, where we have discussed about pump priming and the industrial application of the same. We are going to provide the link in the description box. You can click on that and watch our first episode of real life industrial problems if this kind of problems really intrigues you, because it should intrigue your knowledge. As it is the application of the same. So going straight away to today's topic, what is the flow meter problem that we are talking about? What has happened in the process? So this is a real life industrial problem that I have faced during my working days. So what is happening is a gas is incoming in a scrubber with a high amount of dust load, with high amount of solids. It is incoming in the scrubber. So this is basically a scrubber. And as you know, in the scrubbing mechanism, in a wet scrubbing mechanism, water is brought in contact with the incoming gas in a counter current way, and the gas, hence the dust that is present in the gas is being removed by the incoming water, and the water with a high amount of total dissolved solids, TDS, with a high amount of TDS is coming out and it is being recirculated. There is a continuous process wherein the gas is coming with dust load, changed, varied dust loads, that is varied amount of solids. Depending on the application that it is put to. So sometimes it is coming with a high dust load, sometimes it is coming with a low dust load, and the water that is circulated is taking out the dust from the system, and a clean gas is going out of the system, clean gas out, and the water with the TDS, that is dissolved solids within water, is being recirculated in the system. So there is a slow build-up of TDS throughout, and at times what we do is we blow down some portion of the liquid and we replace that same amount of water that we have blown down with fresh water to maintain the TDS in the system. And this is done at regular intervals. Once we measure the TDS in the system, that the TDS is certainly increasing, it has gone beyond limits, we need to blow down and we need to inculcate fresh air. Even if it is a continuous process, that continuous blow down is taking place and continuous fresh water is taking place, to maintain the TDS in the system, still the TDS will vary because the gas dust load is varying in the system. So varied amount of dust will be absorbed by the water and varied amount of dust will be flowing in the system. But the flow rate in the system given by the amount of liquid is same, because there is a valve here. We have set the opening of the valve, so the valve opening is constant, the valve opening here is also constant, and the valve opening here is also constant. So the flow that is inculcating in the circuit, or circulating in the circuit, is a constant liquid flow. Whereas the problem in this case was that the flow indicator transmitter that was fit in the system here was showing a varied reading or fluctuating reading. So the flow indicator transmitter, flow meter, was showing fluctuating reading. We discussed the same with the instrument department and they tried to find out the flaw in the system, but there was no flaw in the measurement system. So there has to be something wrong with the process parameter because of which the flow here is fluctuating, whereas we have set the valve limits or valve openings the same throughout the process, but the flow is steadily changing. It's not steady, it's changing throughout the process. So there has to be something. First the flow is decreasing, then the flow is suddenly increasing, and then again slowly decreasing. So what is happening? Why is there a very varied flow rate in the system? What is exactly happening? Why is the FIT showing a varied flow rate? Now we need to understand the measuring mechanism of a flow indicator transmitter. Here the flow indicator transmitter, the flow meter, is a differential pressure flow meter. So you need to remember this. So if you know the answer, why is the flow meter showing varied reading, then give the answer in the comment section with proper explanation. Pause the video, think about it, give the answer. Pause the video, think about the system. High dust load flowing, and what is the reason behind the varied flow? I hope you have got the answer. If you haven't, then continue watching this video till the end. It's going to be an interesting discussion, intriguing one. So let me rub out. You have jotted down the points in this system already. So if we come straight away to the working principle of a differential pressure flow meter, what is happening? A differential pressure flow meter. Let us discuss the same with an orifice meter. So an orifice plate is given like this. This is an orifice plate that is inculcated in the system, and a differential pressure flow meter is basically measuring the pressure here, and by looking at the difference of the two pressure, delta P, that is P2, and if I draw this as P1, so P2 minus P1 is my delta P. By this delta P, I am going to predict my velocity at this point of time, V1. Supposedly my velocity at this point of time is V2. So I am going to predict V1 by measuring this delta P. We know the area here is A2 supposedly. We know the area here is A1 supposedly. So if I draw the Bernoulli's equation, considering Z level as the same, Z1 and Z2 as the same, we are going to write the Bernoulli's equation, P1 by rho g plus V1 square by 2g plus Z1 is equals to P2 by rho g plus V2 square by 2g plus Z2 plus HF. So you see that Z1 and Z2, let it be same, it cuts off. So we express this V1, we bring the velocity head terms in one side of the equation, that is V1 square minus V2 square by 2g is equals to P1, or rather P2 minus P1 by rho g plus HF, something like this, where P2 minus P1 is again delta P. So we see we can replace V2, we can write continuity equation. Continuity equation says that V1A1 for a steady state process is equals to V2A2. So V2 is nothing but V1A1 by A2. So if we replace V2 in this equation, it's going to be something in terms of V1 only. So if I replace this, if I rub this and write this equation, final equation, it's going to be V1 square minus V1 square A1 square by A2 square by 2g is equals to delta P by rho g plus HF. Something like this. So we see that V1, if we make V1 the subject of the formula, V1 will be directly proportional to root of delta P by rho. This is pressure difference, this is density. So we often do not consider the fact that it is not only the pressure difference that is the judging factor, but the density is also the judging factor. Now Q1 is nothing but V1 into A1. So Q1 by A1 is directly proportional to delta P by rho. So we see that the flow rate that we are measuring through a differential flow meter, is directly proportional to delta P, that is pressure difference, by rho, the density of the incoming or circulating fluid. So this equation actually is the ruling equation for a differential pressure flow meter. Now we see that the flow rate measured inversely proportional to 1 by root rho, that is inversely proportional to the root over of density. So if the density in the system shoots up, the flow rate will go down. And this is the exact system that is happening here. The slow build-up of the dust in the circulating liquid, is actually causing the TDS to go high. Every time the water sucks in some dust, the TDS goes high and the density of the system goes high. So once the density goes high, the density clearly reflects the flow rate, judges the flow rate. So the flow rate, as the density shoots up high, the flow rate goes down. And while blowing down the system and replacing it with fresh water, the density of the system goes down, and the Q, that the flow rate that is showing, it goes high up. So the flow rate is actually inversely proportional to the root over of density, because of which a changing density fluid will have different flow rates at different point of time, because the density of the system is changing with time, so the flow rate will also change with time. And this is the thing that we often tend to neglect, because we consider that in a differential pressure flow meter, the differential pressure is the only judging factor. It is not the only judging factor when the other parameters are constant, but here the density of the circulating fluid or the density of the fluid that is being measured is changing with time. So the flow rate reflection is also going to change with time, and that is why the FIT was showing fluctuating reading because of the change in density, because of the incoming dust with the gas. Now the dust incoming with the gas is different at different points of time, and that is why the TDS in the system will keep on changing and the flow rate will keep on fluctuating. That the flow rate shown will keep on fluctuating, and this is the problem with differential pressure flow meter in an industry. I think that will conclude it for today. If you liked it, like it, share it with your friends. We'll bring up more episodes of real life industrial problems in the upcoming months. Thank you very much.